Okay, welcome everyone back our class. So this is one of lesson in the in the introduction to the quantum computing and programming. Today we will look more about the last operator. These are adjoint operators. That is if you see in this figure, so you can see we already learned about we have a unitary operator. We learned about the normal operator. Today we will learn more about the Hermitian, the operator, and the adjoint. So what is why we need to do this part? Actually, it's similar like the transform between the traditional and the quantum. Now we need to think more every computation in the quantum perspective. So the adjoint and Hermitian can help operator can help you to transform and to understand how we can the multiply and how we can represent the quantum state in the mathematical way. Okay. The last lesson we already learned. After we have one vector space, we can linear operator. That is we care about the linear, right? Linear operator T from the vector v to the vector v. We transform. And now we have the other kind of operator. It's called the T star. Yeah, T star. Actually different from the linear operator. We have a new symbol. It's a T star. So the adjoint, the operator different from the linear operator is one of two key points. First is after you use the inner products. This inner product, okay? Inner products from the linear operator is equal to transform to the inner products for vector u and adjoint for vector v v. Yeah, this is adjoint. Okay, this is adjoint. Yeah, adjoint. So T star is all linear operator. Yeah, actually this one is kind of to make sure when you transform from this one. Actually, that is one of reflection and sensitive between the two vector and use the new operator. The new operator is called the adjoint. Yeah, remember this inner products. Okay, inner products. Yeah, it's different the quantum. Okay. Standard, yeah. Okay, for example, we have two vector v and v vector w in the same the vector space v. So after we use the linear operator, we use the linear operator. Okay, so we can have a linear. Yeah, this linear operator. We can have the multiply this u and v. So we can have a multiply with a constant, okay? With a u and v, this kind of constant. And now we can see what is the kind of adjoint the operator. This adjoint, right? Yeah, adjoint. So follow our previous definition. We need to calculate by this one inner products for the linear operator equal to the vector and with this kind of linear operator for the next vector. Yeah. So if you follow this formula, yeah, you can see, right? So equal to this one. So you can multiply this one x and multiply this one transform to this one. And you can move to out. So this one move to out and can move this inner products. So after we have these two kind of the order is not enough, but I think this order. So over here, if we look back about the formula, we look back about the previous formula, we can see the t, right? Actually, this guy we have a conjugate for the standard inner products. and multi with v. After we transform, so we can see. So this is how proof. Yeah, how the proof for for the this adjoint operator. And the key point after this is a result for adjoint. Yeah, after you see this one from t vector u, and after you use a function for transform from adjoint operator, so you can have a new the values for the inner products multi with a new vector. Yeah. Okay, here is we will take after we can multiply or we transform transform the one vector, use adjoint operator. We'll think more about how we can represent this adjoint operator in the matrix representation. So this kind of the format. Yeah. Over here we have a basis of vector v, right? We have vector v, and vector v include about the n element, v1, v2, and vn, right? And the vector b is kind of basis, orthonormal, orthonormal, the basis for vector v. Yeah. So it's a matrix. Yeah, matrix representation for the linear mapping. We can equal to the includes the n and the linear operator. This is a linear operator. Okay, this is for h1. So here we have this guy. We have a linear operator. So linear operator, and we have can transform to the x element. So this is a kind of matrix representation. But this one for linear operator. What about the linear? What about the adjoint? So adjoint in the requirement we will have the new chain. Yeah, this adjoint. If you see over here is this is a linear operator, but this is adjoint operator. You can see a difference. You can add star. Yeah, you can add star. This star equal to conjugate. Yeah, conjugate, different in conjugate. Yeah, this adjoint equal to this conjugate. Star outside, that means conjugate the version. This is how we calculate and we prove. Yeah, we prove. So actually over here we can exploit and use a preverse the equation, preverse equation. This one, preverse one, you can check. Yeah, yes, this adjoint operator, that definition. So you can based on that definition, you can calculate and back about this is a matrix, the matrix element, and this kind of formula to calculate about the adjoint operator. Matrix representation for adjoint operator. Yeah, and this is an example. For example, we transform the linear operator. This linear, okay, linear operator between the 3 dimensions in the complex vector. So we have 3 value in the complex vector, right? And over here, this one is after Hobbes. We have Hobbes map, right? This one is Hobbes map. I hope you remember. It's far away. So if you forgot about this Hobbes map, maybe you can check. I think the 3rd or the 4th the lesson in our class. Yeah, you can check about Hobbes map. What is this value? Okay. And based on this one, you can find about the adjoint. Yeah, adjoint. So adjoint. So first, before you can check adjoint, you can check a basis. Yeah, calculate the basis. Because over here we have a three dimension. Okay. So basis 3 dimension equal to this 3 value. Yeah. Okay. 3 1 0 0 or this one, you can the one value can change. Yeah. And remember we have formula to calculate about the conjunct the adjoint. So this one is the matrix representation for linear operator. Okay? Over here do not have star, so this guy have linear. So this guy has value for after you calculate for each one. Yeah, each one for that value for operator. So after that, you can calculate, because you can need to do calculate this part first, right? This part first. After that, you can you use about the conjugate later. Yeah, this one is a kind of yeah, I think so, from previous one. Yeah, from previous one, and after you conjugate, you have this kind of value. Yeah. So after conjugate, so this guy is the total. This one for after adjoint. Yeah. So adjoint operator. Okay. So the last one we have unitary the operator. We have vector v. Yeah. So this guy of t. So unitary the operator. That means we have this part. The the adjoint multi with linear, or linear multi with adjoint. So we have a kind of the number the result. We will have a kind of the identity, the mapping. So we can call if this kind of the linear operator can satisfy this requirement. So it's called the unitary operator. Yeah, unitary operator. Identity mapping maybe that kind of create the matrix with diagonal the value always the 1. Yeah, the 1, something like this. Something like that. Yeah, that's identity mapping. Yeah. Okay. Okay, the property for the unitary operator. So this one is maybe you can check the property. So it's actually the important, this one. Yeah. So it's just the t preserves the vector element. So if any vector u to equal in that vector v, so we can have the after linear operator we have a same length. Yeah, we have a same length. Okay, so we have the other, we have Hermitian, the operator. That is this is spectral K. We have a spectral K. It's called the self adjoint. It means after we have the adjoint operator is equal to linear operator. That's very special K. So that's called the Hermitian. Yeah, Hermitian the operator. Okay, special K. And some property for Hermitian the operator. So we have an agent value for its kind own real value. Okay, and we have this kind of special K. Okay, so now you just we just mentioned about the two key points. Right? We have we have adjoint. Okay, we have adjoint and adjoint operator. And the most important, we have to how we can represent in matrix representation. Yes, that is the most part how you convert it to the part. So I hope everyone can got the point for this part. Thank you everyone. See you in the next lesson.